Hello everyone, my name is Tbaileh. I'm a research engineer with the Pacific Northwest National Lab, and I'll be presenting our paper titled Frequency Response and Congestion Management Using Multi-Terminal HVDC Overlay. So first I want to give a background about HVDCs. HVDCs are used for bulk power exchange, and multiple studies and multiple designs were considered to bring the economic benefits. In this case, for example, we're talking about the US connecting the eastern and western interconnections, and we see here on the right different topologies have been considered, and the economic analysis and the power exchange all been analyzed. However, there hasn't been really any significant work or any work actually developing the actual models in terms of steady state and dynamics, and this is what really the highlight of our work. We combined the eastern and western interconnection models for steady state and steady state power flow and dynamics, and we included these different HVDC topologies, and we did the feasibility analysis, and we also looked into the technical benefits in terms of frequency response and congestion management. And here in this case, we're just highlighting the topologies 3 and 4, since these are the more comparable and the ones with the significant power exchange level. So first, we want to talk about the frequency response results. First, we consider a decentralized frequency controller that we implemented here on the long HVDC lines crossing the seams of the interconnections. Here, it's highlighted with the diamond shape. The frequency controller basically measures the frequency deviation and adjusts the power dispatch or the power commitment level based on this frequency deviation with a certain gain. Looking at the frequency results, we compared the base case with the HVDC topologies without the frequency controller and the topologies with the frequency controller, and we see the orange and the red ones are the ones with the frequency controller, and we see how the frequency control can actually bring significant improvements, especially to the frequency nadir of the system. And here in terms of numbers, we see the frequency nadir got improved in terms of 47% in the case of the microgrid and 36% in terms of the topology 3. So the conclusion that both topologies can actually contribute significantly to improving the frequency response. The other thing that we took a look into is the congestion management. So on top of the frequency control, we wanted to implement a centralized controller that after, and here in this case, we consider after 25 seconds of the contingency, we said, okay, let's look at the power flow in these HVDC links, and let's redispatch them based on a centralized controller to best support the system. In this case, we see, for example, on the top right figure, we see that before the centralized control, the frequency response is the same exactly as we saw on the previous slide, and after the frequency response, basically we were able to redispatch these HVDC lines to the best suit for the system, and we were able to bring the frequency much significantly better than before the centralized control. However, on top of that, we wanted to investigate how the flows in the system are impacted. So we highlighted certain paths that go in WEC in the western interconnection. And in this case, we wanted to see how they got impacted, before the contingency, after the contingency, but before the centralized control and after the centralized control. So here, the top figure here, looking at the topology 3, we see that after the contingency and after the centralized control, both the flows in these paths are increasing. However, in the case of the macrogrid, we see that redispatching these lines, we're actually using the centralized controller was able to bring them back to the original level. So the conclusion that we have that again, both topologies were able to support even further improvement of the frequency response, but having the macrogrid, because it has more HVDC links, and you can redispatch and redirect your flows in more appropriately, can even relieve the system from congestions. So the conclusion and the end of this work is of this presentation that, as I said, bulk power system benefits, bulk power exchange benefits would have been studied, with HVDC lines with different topologies, but no models have, like no steady state or dynamic models have been developed. So this is what we worked on in this project, and we did the feasibility analysis, and we investigated the technical benefits in terms of frequency response and congestion management for different HVDC topologies. The highlight also that we found that the HVDC microgrid brings additional benefits, considering that it has like more lines and it covers better area, and you can direct your flows better with this HVDC network. More things to investigate. We would like to evaluate different HVDC technologies and different designs. We would like also to look into more detailed modeling of the converters, and we can also investigate a more optimized control for for the redispatch and the centralized controller. Thank you.